Hi everyone, this is going to be an exciting video because this is the first time, if you're watching the videos in order, the first time we're going to see an organic chemistry reaction. I don't consider acid-base reactions organic chemistry because they mainly deal with inorganic compounds. But in this hydrohalogenation, we are going to take an alkene and do what's called an addition reaction. We're going to look at this in detail, and we're going to see that it goes through a carbocation intermediate, and we're going to talk about different aspects of this reaction and how we could predict, regardless of what alkene we're given, what the product will be, which is really a very powerful skill to have, to be able to look at a molecule, throw in a reagent, and understand where exactly on that molecule the reaction will happen. Okay, so enough of the intros. Again, we're going to look at hydrohalogenation. We haven't talked about resonance. That will be the next couple of videos after this one. Well, I might as well just jump right into it. The name. When I think, or when I study a new reaction, I give it a title. And it may seem like extra information, especially if your professor won't grade you or won't test you on whether you know the names of these reactions, but I think by naming them it keeps them well organized in your head. Okay, and also this hydrohalogenation means that we add a hydrogen and a halogen. After that, I typically give a general reaction. Okay, well, it will be a specific molecule, but it will be our representative reaction for this hydrohalogenation. Now you could put the reagent above the arrow, or you could put it next to the alkene and put plus. It doesn't really matter, it's just preference. Both of these are starting material, but I like to think of this as the starting material, the main starting material, and this is the reagent that converts the starting material into a product. Okay, so we're going to keep an eye on these three carbons. Okay. Without telling you any details about how this happens, the product we get is, let me grab my blue pen. Okay. Product we get is this. And if you are very good at line structures, you would realize that the hydrogen goes on this carbon and the chlorine goes on this carbon. In these types of reactions, typically you're going to add something to each of the carbons of the double bond. So this is also called an addition reaction. We're adding to the double bond. Addition, or add to double bond. In contrast, it's not a substitution. We're not substituting any atom for another atom. We're just adding. And what happens is that both of these carbons now have 4 single bonds. Okay. So I mentioned that the chlorine goes on the central carbon. Okay. Let me show you the product that we don't get, although you may think we get it, and that's this one here, where the chlorine goes on the other double bond carbon. This has a special name, this idea where you form one constitutional isomer over another, and that's called regiochemistry. Or we'll call it regioselective. It's regioselective because the reaction preferentially makes one constitutional isomer over another. So these are constitutional isomers, right? They have different connectivities. Reaction prefers one, and I'll put in parentheses, or a set of constitutional isomers over another. Another one or another set. Okay. But right now, really, we only have two situations. The chlorine goes on the central carbon, or the chlorine goes on the end carbon. Okay. The next thing normally that I like to put on a study sheet for a reaction, and let me just circle this, hydrohalogenation, is the mechanism. Okay. So yeah, I'll put here mechanism. Okay. Mechanism. The mechanism shows the movement of electrons to make intermediates and make products. There's actually two steps in this reaction. We started with the double bond, or the alkene. And yes, all of this you have to know for the exam. You have to know what's called the mechanism. Or some people call this a curved arrow formalism, but we're going to use what's called curved arrows. And it's possible that we've talked about these before. You start your curved arrow from a source of electrons. Well, I have HCl. Depending on your professor, they may want you to put equilibrium. I normally don't unless it's a acid base or a proton transfer. Technically, we do have a proton transfer, but it's really up to the preference of your professor. I don't mind if my students use just a regular arrow instead of equilibrium. So this is going to look a little strange if you've never done this before. Start your arrow from the middle of the double bond, and you grab the hydrogen. And then this bond breaks because hydrogen can't have more than 2 bonds. Right now, I'm giving you a lot of detail. The beauty of this is that the other alkene reactions, the vast majority of them are going to be addition, and we're just going to change the reagent to add different things. So it's going to seem a little slow at first. And actually, we're only going to talk about this one reaction in this unit. The other reactions of alkenes we're going to talk about in Unit 5. But I wanted to introduce this reaction as soon as possible. Okay. All right. So I said a lot. Let's focus back on our mechanism. So this is going to be interesting because the molecule chooses to put the hydrogen on this carbon. And we'll explain why in just a bit. But this carbon is naked. It only has 3 bonds. There's a hydrogen here, but when we use these electrons to make a bond to hydrogen, we actually have a carbon only 3 bonds. It's going to take some time to get used to that, but soon it'll be automatic. When you get rid of this double bond by adding something to the end, it's this carbon in the middle that's naked. Okay, and we're going to form this carbocation. I typically insist that you draw all the products resulting from a step. Okay. Now, is this going to be the final product? No, we don't see chloride ion anywhere. This is the main organic product, but in the middle of the reaction, during its mechanism, you do form chloride. And then what happens? Chloride comes back and attaches to the carbon. And that's it. That is our mechanism. What do we consider this? How many steps? We consider this 2 steps. 1, 2. If I ask you for the mechanism, this is what you should draw. Okay, in blue and pink. I like to use pink just so my arrows are really noticeable and I can memorize them a little bit easier. In green, I'm going to give you a couple more notes. Pi bonds are considered electron rich. Okay, if you think about the geometry of a pi bond, oh, I have a pi bond right here. All right, so I don't. Oh, this model might actually be propene. This molecule right here. So I don't have the 2 blue curved arrows. Okay, because what I'm doing is instead of that, I'm showing the p orbitals, and you know that a p orbital makes a pi bond. So there's a pi cloud above and below the 3 carbons, and it's apt to attack and attach to another atom. And yes, some texts, I think a lot of textbooks, almost all professors say the word attack. This is the attacking arrow. And we typically say, oh, before I say that, molecules that are electron rich are typically what's called nucleophiles. Nucleophiles. A nucleus is typically positive, right? Because you have protons and electrons. Oh, protons and neutrons. So what do you think a nucleophile is? A nucleophile is a lover of that positivity. Well, if this is electron rich, which is electron deficient, electron rich means you would think of it as partial negative, it's being attracted to something that's partial positive. And we know that from the polar bond, chlorine is partial negative and hydrogen is partial positive. So we're going to say the nucleophile attacks. I'll abbreviate it NU. Attacks. And what do they call this? I don't know if I said it. This is called the electrophile. They come in pairs. Nucleophile is attracted to electrophile. Electrophile loves electrons. Okay. Again, don't worry too much about the terms right now. You have to exercise your brain to be able to draw this. Now, honestly, this will take 3, 4, 5 times with your notes before it becomes automatic without your notes. Okay. What else can we say about this mechanism? We make a carbocation, and we can also say, and we've heard this before, opposites attract. Yikes. Opposites attract. We had opposites attract here. Electron rich, partial positive. Negative, positive. So these areas of electron density that are rich and poor, they could be seen in several different ways. They could be a partial positive or a full positive. Okay. This is your final product. Is there anything else I want to say about this? Why? Okay. So again, this is your answer, but we really got to explain why this is occurring, because what carbocation are we not making? If you know that this product came from this carbocation, okay, where do you think this product potentially could have come from? It came from the carbocation where the carbocation was on the last carbon, okay, because that's where the chlorine was attracted to. Theoretically, if this was a product, but it's not. So what that tells me is that during the mechanism, this is not made, most likely because it is not stable. I haven't gone over yet why, but that's part of our video, carbocation stability. Okay? Alright, let's go back. Okay, so the task for me in the next 5 minutes is to explain why the carbocation is in the middle and not at the end. But to be able to talk so you understand what I'm saying or what carbon I'm referring to we have to learn about something called primary, secondary, tertiary, quaternary carbons. Yeah, we can have quaternary. Alright, so a primary carbon is it looks like this. Well, let me draw you a whole bunch of different carbons actually. This is easy. Let's look at this carbon right here, the one with the dot. This carbon is called a secondary carbon. Okay, don't spell it out, this is abbreviation, but when you say it, this is secondary. Okay. Let's see if we can find a pattern. This one over here. That carbon is primary. Do we have a tertiary? Do we have a 3-er? This one. This is a tertiary carbon. And oh, we need one quaternary. Quat, meaning 4, quaternary. The trick is, let me just put dots. The trick is, ask yourself how many other carbons are attached to that carbon. So this carbon here is primary because it's attached to one other carbon. This carbon here is secondary because it's attached to 2 other carbons. What about this? What kind of carbocation did we make in the mechanism? So what kind of carbocation is that? That is a secondary carbocation. This is a secondary carbocation. Not what? Not a primary. Primary carbocations look like this, because that carbon is attached to one other carbon. Okay, so that's interesting. You know, when they're first looking at this reaction, studying it, I don't know if they were able to predict this, but what were they able to do? They were able to analyze the products. And when they analyzed the products, they were said, that's a little peculiar. We don't get a chlorine on this carbon here. Let's propose a mechanism and then try to understand why we don't get a chlorine here. Probably because here now that we have the terminology, we could say that secondary carbocations are more stable than primary carbocations. And since this intermediate is more stable, it's going to be the one that's made, and then it's going to carry forward to form the final product. So let me show you, or let me draw out the trend. And let's do a couple more examples. Okay, so the trend is, for now, tertiary, carbocations. Yeah, I'm not going to write the word carbocations all the time. Greater than secondary. Greater, what do you mean by greater than? Greater stability. Okay, so you have a greater than sign, but go ahead and put the parameter. Greater stability than secondary, greater stability than primary. How come I don't have quaternary carbocations? A quaternary carbon can't have a carbocation because it already has 4 bonds. It has to have 4 bonds. Okay, so there's no such thing as a quaternary carbocation. Why? Before we go back to the reaction, why is this the case? Why is this the case? Well, we have to envision again our p orbital. Okay, let me just flip it this way. Let me take here's a molecule right there. So we have p orbitals. Why am I talking about p orbitals? I don't see a double bond when I have a tertiary carbocation, because we have this. Okay. Let me give us an example of a tertiary carbocation. Okay. So that's tertiary. But now I'm going to look at the orbitals. When I want to look at the orbitals, I got to know what the hybridization of each carbon is. Remember the trick? Hopefully I talked about this previously. You count balloons. A balloon for me is an area of electron density. It could be a lone pair, it could be a bond, it could be a double bond. A double bond for me counts as one balloon. So you count these areas of electron density, and that will give you the hybridization. For instance, if this is, let's do this. If this is, how many balloons does this carbon have? Well, you got to remember that it has 3 hydrogens as well. It's a tetrahedral carbon. So this is 4 balloons, sp3. The thing with a carbocation is it doesn't have 4 balloons. It doesn't have this lone pair. It only has 3 bonds. 3 balloons is what? sp2 hybridized. Trigonoplanar. Why is that important? I thought we were talking about stability. So what if it's trigonoplanar? Because you should remember that when you have a carbon that's sp2, what do you have? You have an sp2 orbital this way, an sp2 orbital here, and an sp2 orbital here. Okay, trigonoplanar. Sorry about the size. Those should have been equal size as this one. sp2. But with an sp2 atom, you have one unhybridized p orbital. Okay, so when I draw a carbocation, I'm not going to draw the sp2 because I'm not concerned about that. I'm going to just draw, there's going to be a methyl group here, a methyl group down here. I'm looking at this molecule right here. Man, I'm kind of messed up. A CH2 here and a C. Okay, now I'm going to put 3 hydrogens here. But what about the other carbons? I'm literally going to draw the hydrogens. Okay. This is not. Man, I messed up this geometry a little bit. Doesn't matter. We can still introduce this concept. Where's your p orbital? See, this carbon only has 3 bonds. It's this carbon in the middle. So it's positive, but I'm not going to put a charge. I'm going to know it's sp2 hybridized, and I'm going to draw the p orbital. And I kind of messed up because I should have tilted this bond a little bit to the right. But there's your p orbital. It's still a p orbital. And I don't know how many professors like doing this, but I'm going to remind myself that's the carbocation because technically that p orbital is empty. That p orbital is empty. There is no electron in my line structure or my Lewis structure, but that p orbital exists. The fact of the matter is, charged molecules are inherently unstable. So if you could reduce that charge somehow, or if you could spread it out, either way, you can increase the stability. These hydrogens can donate electron density. And you notice that the more alkyl groups you have around the carbocation, the more likely you'll be able to share electrons from what is this? The sigma bond. So this is called hyperconjugation. And it's a sharing of electron density from a sigma bond, from a neighboring sigma bond. Geometry-wise, they're pretty lined up. Okay, so sharing of electron density from the sigma bond. That's why a primary is very unstable, because what's a primary? A primary carbocation doesn't have maybe these 2 groups. It only has one R group. So what's the other bonds? The other bonds would be hydrogen. Like if this was a hydrogen, where my finger is, and this one a hydrogen, then really the only hyperconjugation I have is with these bonds on the left. But this one has hyperconjugation with all of these carbon-hydrogen bonds. Okay. So I'm running out of time, but let's do some practice. Okay, that molecule. How about this molecule? And maybe a ring. Let's try a ring. When you do hydrohalogenation, you could use HBr or HCl or maybe HI. Okay. Remember, it doesn't matter whether I put the reagent as a plus reagent or over the arrow. Doesn't matter. I'm going to go through this a little bit fast. I'm not going to draw the mechanism, but think about what you need to do. You need to make the more stable carbocation. So you can always go back to the mechanism that we've shown before. Okay, you have to practice this. All right, but let me show you that we can think about this without literally drawing the mechanism. Which carbon is more substituted? It's this carbon right here. So if we make a carbocation right here, it would be tertiary versus primary. That is where the bromine is going to go. I like to put these two arrows, okay? For me, that's a habit, to remind myself, for the vast majority of cases, your chlorine or bromine or iodine will be on one of these two carbons. In this case, it will be right here. Okay? And then for this case, I'll give you a time, or you could pause the video. Iodine right here. They studied this reaction. At first they didn't predict this, but they realized over and over again the halogen goes on the more substituted carbon because that's where the carbocation was. You could draw the mechanism for each of these and ask yourself, where's the carbocation? Where's the more stable carbocation? Now, there's more complication to this, and we'll probably see that in Unit 5, but I do want to tell you one term. That term is called Markovnikov's rule. Markovnikov's rule. You make the product that comes from the more stable carbocation, or the major product comes from the most stable possible carbocation. A little floppy. For the most part, the carbocation you got to choose. Is it going to be on one of the carbon of the double bond or the other carbon of the double bond? So you have two choices. I mentioned that there's complication. That's because there's a thing called carbocation rearrangement. But we'll revisit hydrohalogenation in Unit 5, and then we're off to the races, okay? Doing a bunch of addition reactions. Unit 5 is the one where you have between 9 to 12 reactions, and you have to do what? You have to do all of this. You know how to do the product. Heck, they could cover up the middle and say, what is the reagent to do this reaction? You got to know the mechanism and all of the little details for each reaction, or at least for most of the reactions. Now there's one last thing. Let me take a look at this molecule here. Okay. This is very interesting. It came, sorry, I'm going to have to rush a little bit. It came from this intermediate, a secondary carbocation. Now, I'm not going to draw the mechanism because I don't have this bond to break. When you draw a mechanism, you literally have to show every bond formed and every bond made. Alright, so that's why I have to draw this bond. Normally, right, when you just draw in the general reaction, you don't draw that bond. Came from this secondary carbocation. When the chlorine comes in and attacks, technically, you know that carbocations are sp2, trigonal planar. That's another word for trigonal planar, flat. So that carbocation, the molecule is flat. So actually, these three carbons are in the same plane, right? And we have a p orbital sticking out and towards us, out and away from us. Don't worry about the visualizing geometry. Just know that this is flat, and technically, your chlorine could come in from the front or the back, and we get a mixture. Technically, we have a mixture. This is called a racemic mixture because it's a 50-50 of, you're not going to be able to escape stereochemistry, people, enantiomers. Enantiomers. Racemic. A lot of times your professor will say, does your reaction make a racemic mixture? Now, why doesn't this make a racemic mixture? Because this has no enantiomers. You have to make a chiral carbon, a chiral center, to possibly have R and S. This molecule over here, you know that's not a chiral carbon, and there's no R and S. So ponder that. Let me zoom out, and that's our first reaction. Okay, there's plenty more to come.